Welcome to our Novel Forest Data and Applications session, Part 1. I'm Tanya Birch, and today we're going to explore NASA's Global Ecosystem Dynamics Investigation, or GEDI mission with Dr. Laura Duncanson, and learn about an application called Obi-Wan, which stands for Online Biomass Inference using Waveforms and Inventory. Dr. Laura Duncanson is a remote sensing scientist with a focus on using LiDAR to map forest structure and biomass. She's an assistant professor at the University of Maryland, College Park, and she serves on the GEDI and ICESat-2 science teams. Dr. Sean Healey works for the National Forest Inventory, which is managed by the U.S. Forest Service. He leads development of the Obi-Wan application and coordinates GEDI's statistical approach to estimation of forest carbon over large areas. I'm excited to welcome to our virtual stage Dr. Laura Duncanson and Dr. Sean Healey.
All right, thanks very much, Tanya. It's such a pleasure to be here. We're really excited about Google Earth Engine and the amazing things it's doing all over the world, enabling science and applications, and can't wait to see what kind of stuff people do with GEDI in the platform. So in this presentation, I'm going to start by giving a bit of a mission overview of what GEDI is, why it matters, and importantly, how we use it to estimate forest above ground carbon or biomass. I'm going to be giving a kind of hands-on example of using a biomass model for predicting biomass for one waveform in the Brazilian Amazon. And then I'm going to be passing it over to Sean Healey to talk about GEDI's gridded product and also the very exciting Obi-Wan tool following along that Star Wars theme. And then we'll pass it back to me to talk about what's next with the mission. All right, so we all understand that forests are a really important part of the carbon cycle and of climate mitigation through hopefully improved forest management. So there's this huge link between forests and carbon and climate change. But at this point, we still don't know with great certainty how much carbon is stored in Earth's forests. And we don't know that because we've never had the right data to map forests in 3 dimensions at a global scale until now with GEDI. So GEDI is providing this amazing new data set that we're really hoping will fill this critical carbon gap so that we know not only how much carbon there is in total in the Earth's forest, but how it's spatially distributed. And that will allow us to be able to fairly accurately quantify how much carbon is being lost to the atmosphere through deforestation and degradation, and hopefully how much carbon is being sucked back into those forests through regrowth. So the GEDI mission, as I said, is the first satellite LiDAR system designed specifically to measure forest structure. So we've had LiDAR in space before, but it's never been fit for purpose for measuring forests in 3D and forest carbon. This is a really exciting time in the mission. We are over 10 billion observations and counting. So this is a lot of data, a lot of 3D data. And it's as I said, it's kind of fit for purpose for forest structure mapping and hopefully will be used through fusion for monitoring. So it's a full waveform near-infrared LiDAR system. I'll talk about that in a second. And it was launched on this very happy day back in December of 2018 to the International Space Station. It started collecting science data around April of 2019, and it's still collecting data. So it's still firing lasers at the Earth's surface and making these 3D measurements. As I said, there's over 10 billion right now. And it's growing every single day, right? So it's really exciting. Those waveforms are used to estimate the elevation of the Earth's surface, both through topographic mapping, but also you can even map the topography under dense canopies, which is really exciting. But it's really focused on forest structure. So we've got products related to canopy height, canopy cover, and the newest one, above ground biomass, which has been released relatively recently. There are 18 months at this point that are publicly available, but there's more data that's going to be rolling out in the months to come. Very exciting is that the mission has been formally extended until at least January 2023. So originally this was only a 2-year mission. It's kind of like renting an apartment versus buying a house. When you're up on the ISS, we don't have our own satellite. So we've extended our lease until at least 2023. So that means a lot more GEDI data for science and applications. All right, so for those of you who aren't very familiar with the GEDI mission, it's a LiDAR mission. So we've got 3 lasers plugged into about a refrigerator-sized box on the side of the ISS. One of those lasers is split into 2 beams that we call our coverage beams, and the other 2 lasers are full power beams. So we've got these 4 laser beams coming down toward the Earth's surface, and they're being optically dithered back and forth to make these 8 ground tracts. So when you look at GEDI data, you'll see these 8 ground tracts under the ISS. And those are comprised of these 25-meter diameter samples. And so each of these, a laser illuminates 25 meters and returns what we call a full waveform. And so this is under the orange squiggle here. This is the full waveform data that is the kind of core GEDI observable. And so the photons that bounce back off the top of the canopy get back to the ISS before the photons that bounce back from the ground. And so the difference in time is translated to a distance that gives you the canopy height between the first and the last photons reflected. And then that area under the curve, under that orange squiggle there, that tells you how much kind of bulky vegetation there is. And we describe these orange squiggles, these waveforms, with waveform metrics, and we use those metrics to predict above ground biomass or forest carbon. So just to speak to the sheer volume of data that we have with GEDI. So this is orders of magnitude more satellite LiDAR than previously available already, and we're still collecting data, right? So we've had some forest biomass maps created in the past, and a lot of them have used satellite LiDAR data from ISAT's GLASS. So one, it was designed for ice. That's why it's called ISAT. But also there was just a very sparse sample of these data sets. So you can see here, you can barely see them on this chart, comparing the number of LiDAR samples used to make those old biomass products compared to what GEDI's already collected. So we really think that with the sheer magnitude of data that's designed specifically for forest structure here, GEDI is going to be able to produce much more accurate biomass products than have been previously available. So just before I talk about what the actual biomass products are and how we create them, we'll just take a pause and tell everybody what biomass actually is. So we often use biomass interchangeably with carbon, and that's because they are extremely related. So we don't have the ability to actually weigh trees to measure their mass. We can't coerce them onto scales. But if you were to cut down a tree and you were to dry it, about half of the mass, the dry mass of that tree, is pure carbon. So when we map biomass, we're mapping above ground. So nothing in the soil, we're mapping the trees above ground and their woody components. And the mass of that, roughly divided by 2, is the amount of carbon that's stored in those trees. So when we're talking about biomass mapping, we're talking about trees above the ground, the woody components, and that's roughly equivalent to twice as much carbon as there is in those forests. All right, so for us, making biomass estimates with GEDI waveforms, we realized pretty early on in the mission that we all know that the best way to get an estimate of biomass is literally going out and measuring trees, right? And if we can't cut them down, which usually we don't, we measure them physically. So like professionally tree hugging, wrapping measuring tapes around trees, that's how we get an estimate of biomass. And so of course, we're not doing that from space, right? We're not able to go out and hug every single tree on the planet. And we weren't able to sort of do this massive field campaign all over the world and collect samples in all these amazing ecosystems in the relatively short GEDI mission lifespan that was originally 2 years. So we knew we couldn't do a whole massive field campaign. So instead, we really relied on the international research community to contribute data. So people have contributed their field plot data where they went out and they physically measured trees, as well as their airborne LiDAR data. So if a field plot had an airplane fly over it and collect airborne LiDAR data at the same time, same place, then we can take that airborne LiDAR data, simulate GEDI with it through a waveform simulator, and then build these empirical models between the field plots and the simulated waveforms as if they were on-orbit waveforms. And so that's our general approach to estimating biomass with GEDI, is we built all of these calibration equations in advance of launch even, and we're applying them to the on-orbit GEDI data. So these are extremely simple equations, and I'm going to show you a real example of applying one of them in a second. So this is our training data set. And I wanted to show this because we want to be honest about where we have a really good sense of how accurate we are and where it's still a bit TBD. So all of these orange and blue circles here are where we have people going into the field who have also the airborne LiDAR component, and we use those data sets to train our models. So we've got pretty good coverage in North America and some parts of South America, and some parts of Europe, but we have massive data gaps in some areas. We don't have really anything in Central Asia at all. South America is pretty sparse. West Africa is pretty sparse. So there are some places in the world where we know we can do better if we had more training data. But with the training data that we do have, we divided the world up. We asked, should we just create one global model to rule them all to translate these waveforms into estimates of carbon? And of course, trees growing in different places in the world look different. So you can't apply the same model to trees in California as trees in, as the Amazon and dryland systems, etc. So we divided the world up into very, very broad, simple classes of plant functional type. So for example, EBT here is evergreen broadleaf trees. Grassland, shrubland, woodland is that GSW class, which is kind of a catch-all for kind of low biomass dry forests. And then we also divided the world up by geographic region, which is roughly continent. So in the end, these stratified models outperformed our global models. And so, as you break the world up, you get better and better as you get more and more refined. At some point, we're essentially just data limited, and we can't split the world up any finer. But this is our sort of suite of classes that we use to predict biomass. So here is an example of one of those models. This is the evergreen broadleaf trees model in South America. And it is super simple. This is not a fancy machine learning algorithm. This is a simple linear model, a simple OLS model. So here we're predicting the square root of biomass, above ground biomass density, AGBD here, as a function of two waveform metrics. One is RH50 and one is RH98. So these RH metrics are in the level 2 product for GEDI that's been out for quite a while. RH98 is roughly equivalent to maximum tree height or maximum forest canopy height. And RH50 is roughly equivalent to about the mean. So it's the height below which 50% of the waveform energy has been returned. And so these metrics for this waveform, this is a real on-orbit waveform from the Brazilian Amazon. We've got a forest height here, RH98 of 29 meters and an RH50 of 19 meters. So plugging those into this equation for this waveform, for this 25-meter sample of forest from GEDI, we have an estimate of 149 tons per hectare of biomass. And of course, we have an uncertainty with this as well. But that's it. It's very, very simple. We have a set of models. We apply them to our 10 billion and growing waveforms. And then I'm going to pass it over to Sean to talk about how we translate those into gridded products.
Great. Thanks, Laura. I just need to make it clear that the first couple of things I'm going to be talking about involve the GEDI mission itself, standard products that are coming out of the mission. After that, I'll be talking about an app that you might say is part of the GEDI ecosystem that uses GEDI data for a very specialized purpose. But first, the standard products that GEDI is producing, one of which is estimates of forest biomass at 1 kilometer scale. So for every 1 kilometer grid cell in the latitudes that GEDI covers, GEDI is making an estimate of mean biomass. And as Laura said, GEDI doesn't image the whole planet. It basically samples the planet in tracks and of waveforms. And so our approach, as you can see here with this 1 kilometer cell, is GEDI is not seeing all of the heights in that 1 kilometer cell, but it does see a sample. And like any kind of marketers, or I work for the National Forest Inventory, we have a large sample of inventory plots across the country. A sample gives us a pretty good idea of what is in this 1 kilometer grid if we have enough samples in there. And so what GEDI is doing is taking a sampling approach where we're using statistical theory to allow us to estimate not only what is the mean biomass from all of the places where GEDI measures biomass with the equations that Laura just talked about, but also to estimate the uncertainty that's involved with the sampling error and also the modeling error. That there's error in the models that Laura just talked about. So we can put those together, and around the world we make a 1 kilometer estimate of mean biomass and the uncertainty of that mean. By the time you're seeing this, the first version of that map will be available on NASA's LPDAC. I think it's the LPDAC. And basically what that is 1 kilometer grid cells with an estimate of biomass and an uncertainty around that biomass. And if you were to look closely, a lot of the 1 kilometer cells don't have an estimate because GEDI hasn't seen that 1 kilometer grid cell enough yet. But the great thing about the extension that Laura talked about is, every day GEDI is getting more samples. So we're filling in more and more of those grid cells. And the grid cells that have been seen before, it's just more samples in there. So our estimates become more precise. Okay, so this is a GEDI standard product. It's called L4B gridded biomass. Okay, now I'm moving on to sort of the derived application. Obi-Wan stands for Online Biomass Inference Using Waveforms and Inventory. And basically the idea here is that we're creating customized, we're creating carbon reports for customized areas. There are a lot of frameworks, from market-based frameworks to aid-based frameworks to national commitments to the Paris Agreement, all of which sort of incentivize protection of forest and maintenance and increasing forest biomass as a global climate service. None of those frameworks reference 1 kilometer grid cells. So, the relevant scale is whatever the user says it is. And usually that is a very irregularly shaped forest reserve or some other kind of piece of property, or maybe it's a country. So what Obi-Wan basically does is allows a user to define an area of interest, uses GEDI's waveforms, uses GEDI statistics, and also uses the models that Laura talked about for inferring or predicting biomass at each of the footprints to deliver an estimate of biomass for whatever the area of interest might be. We are close to, but have not yet released Obi-Wan, but coming soon, it will be hopefully fairly useful for forest managers around the world. The back end of Obi-Wan really relies on, I guess this is where we intersect with, Google Earth Engine. It really relies on a GEDI asset that Google has helped us ingest. Google is really a big part of the back end of Obi-Wan, and give a paper down at the bottom there that you can read all about that asset. Okay, another cool thing about having, besides supporting Obi-Wan, another cool thing about having a GEDI asset set on Google Earth Engine is that we can now easily combine GEDI with all the other sorts of spatial data that Google Earth Engine hosts. We did an exercise where we made models of forest height from Landsat. Usually, it is not easy, and in fact is pretty impossible, to predict forest height very well with Landsat. Landsat doesn't penetrate the canopy, it's just looking at the top. But because GEDI is collecting so many billions of shots and it's so dense, we can make really localized models that allow really pretty good prediction of forest height. And in fact, that will be that kind of map will be one of the targets for this extended mission. I think Laura might allude to that.
All right, thanks, Sean. So I'll just do a quick wrap up for what's new and what's next for the GEDI biomass mission products. As I said, the footprint level L4A product, this is already online, and both of the sets of the footprint level and the gridded products are going to be available through NASA's Oak Ridge DAC, ORNL DAC. And so the footprint level products have been online for a couple of months. The gridded products are either coming soon or they're already available, depending on when you see this presentation. And we want to really clarify that this is not sort of like the final answer about how much biomass there is in the world, right? So we are going to be getting better and better as we have more GEDI data that Sean just spoke about, but then also we're going to be improving our models in the future. So we're going to be putting out future versions of the L4A and L4B products as we have better and better models. So we as a science team already have some plans for how to improve these. We're going to be adding cover as a predictor soon. So cover is from GEDI's L2B product. We're exploring some other modeling approaches, such as machine learning, which is largely from Jim Kellner's group. And we're also looking at better allometric models for estimating biomass better in the field, which we imagine will then improve our estimates all the way up to the satellite data. But the main thing that we are really looking forward to are incorporating new high quality training data into our model fitting. So as we showed in this map on the top right, there are a lot of places in the world where we don't have any training data. So we're working to find new partners, hopefully some people watching this presentation who have access to field data and airborne LiDAR in some of these places that are undersampled. So this is a living database. As we get those data sets in, we can refit the models, we can make them better and better, which will reduce the uncertainties in the footprint level and gridded products. So we really do think that this is a global community effort, and we hope to engage with many more people. Sean, do you have anything you want to add to wrap up? You're muted, sorry.
Thanks. This is an exciting time, Laura, because we've spent 2 years or more than 2 years collecting data, putting data out there, processing data, and it's only really now that the data are really penetrating to users, and a lot of the exciting applications are only now emerging. So, this next period, I think, is going to be a very exciting time for the GEDI mission. Just want to say thank you to Google for the opportunity to present to you. It's an interesting and vibrant community, and one that's good for us to interact with.
Thanks. Yeah, and also a big thank you to everyone who has participated in contributing CalVal data to the GEDI biomass modeling effort. And we can't wait to see what people start doing with GEDI data in the Google Earth Engine platform.